Pleased me to welcome Kenneth Tan from Sardina Systems. Kenneth.
Thank you, everyone. Thank you, everyone, for coming back after lunch. I'm the unfortunate after lunch guy, so hope that you're all still awake. So today, I want to talk to you about managing cloud infrastructure and what do we do to increase efficiency and increase reliability on these systems. So now, resource management in cloud, they share some similarities to what we see in traditional HPC, and, but they also have some differences. So I want to touch on the placement problems of workloads, how do we rebalance workloads within the cloud infrastructure, and how do we optimize resources on the system from an operator perspective. And then we're going to talk about how do we increase reliability of systems, of such cloud systems. So now, in cloud, it's very important to look at the operator-consumer relationship. So also, the operator relationship, when it's very tightly coupled, there is greater trust between the parties. There is a lot more things that an operator can do than in a loosely coupled situation. So now, when we look at a tightly coupled situation, then resource contention issues is less of a matter. And if, on the other hand, you have a loosely coupled situation, then the trust level is a lot lower. But for the operator, this is both a problem and an opportunity. And we'll come to more of this in a moment. And at times, I also get asked about, hey, what about containers? What about containers? Containers are not new stuff. I mean, these things, in terms of the concept, they go back decades. So, but essentially, what's a container? Container serves two key functions. First, as a packaging system, and second, as a kernel slicer. So, if it's kernel slicer, then the question is, which kernel? And here, you're looking at the host kernel versus VM kernel. And sometimes I talk to customers, and customers say, well, you know, we'll run everything on the host. Does this present a problem? It could do. So there's escape risk, and for operator, this is high-risk stuff. So most of the operators that I deal with, they don't do this. They'll put the workloads inside a VM and let the containers run inside the VMs. So here, you're slicing a VM's kernel. And if there's any escape, there's escape to one single kernel, which is dedicated for that particular service consumer. Now, with that, look at the VMs versus the containers, the host kernel versus the VM kernel, and there are various other things that come into play. For example, with VMs, you have live migration, which is often very, very useful. And this also has to take into account how you fit into the client organization. So, loosely coupled versus tightly coupled organizations. And sometimes we see the often cited loosely coupled environment, so a commercial service provider or a national service provider providing service for broad user base. And sometimes we see this also within one single organization. It could be one very, very large organization, for example. Yeah? And so, indeed, as I mentioned a moment ago, if you have loosely coupled situation, you practically see the operator putting the workloads inside VMs and you cleanly manage the segregation. So, whereas the converse is that in a closely coupled environment, you could put them together. So this takes us to another view, which is that, well, Kubernetes resource management, for example, it basically boils down to a VM management problem, VM resource management problem, right? And, but then, is it a resource management problem from whose point of view? Not necessarily the service consumer's point of view. Got to be paying attention to the operator side. So, come back to operator versus service consumer. Now, the operator's job is to keep the infrastructure running. The operator doesn't get involved with what's happening inside the service consumer's environment. Conversely, the service consumer is only interested in using it. Doesn't care about how the environment is provided. So, for resource management, whose problem is it? It's the operator. Because the operator is the one that actually runs the kit. So the operator is the one who actually forks out real cash. They are the ones for whom money matters. So, going back to Kubernetes resource management, so which kernel? Well, host kernel or VM kernel. And we've got to be looking at managing resources from the host kernel standpoint. And then, for the larger organizations that we see, when you are placing VMs, you end up facing the question of where the VMs are going to go. And these VMs could be the VMs that are running Kubernetes as well. Okay? So, we have these two questions: how to place the VMs and how to continuously keep the environment in a balanced manner, in an optimized manner. So, first, we go collect data. What data do we collect? Well, we need to know not just what's the CPU load. We want to know what is the resource consumption of each of the VMs in which part of the processor. We also want to know what each of the VMs are doing in each part of the memory hierarchy. Does this sound like a benchmarking problem to you guys? Yeah? And so we collect this data, collect lots of data, And then, basically, we automate the process of making decisions. And now, for how do we place the VMs, and how do we deal with the resources in the system? So we have this issue of uniform versus dense situations, and can see whether we're talking about a fault tolerance objective, a resource utilization perspective, or the communication and management complexities. So, if we're uniformly distributing the workloads across the system, we get the profiles as you see in the table there. Conversely, if we pack them densely, we get certain benefits. So, as I mentioned, we have two key types of problems: a placement problem and rebalancing problem. So, placement is whereby you have a new VM coming in. Sorry about the slides. The placement problem text was a little bit too high. So, the placement is given a new request for a VM. Where does the VM need to go? We've got a farm of however many thousand physical servers. Where does this new VM need to go? And then the other side is the rebalancing problem. So the rebalancing problem is whereby, given the workloads within the system, we have the data. We have the data about how that particular set of VMs are behaving. So how do we optimally pack them onto as few servers as necessary so as to keep the workloads running, but avoid wastage across the facility? The service consumer isn't aware of this. Remember, the service consumer runs their workload inside the VM. This is on the infrastructure side. They don't know this. But for the operator, if you're able to do this, there are some very interesting benefits. Principle of which is that given the set of hardware, which for an operator it costs you money to buy, and it costs you money to keep the hardware running. So given that fixed cost, if you optimally pack them, optimally place them, you can run a lot more workload on the system. This is like kids and their toy boxes. Sometimes, depending on how you put the toys in a toy box, it may fit. Some other times, you put them differently, they may not fit. Same set of toys, same box. Yeah? And another view of this is that for the operator, if you can optimally pack them, you can run a lot more workloads on them. And if you are a revenue-generating operator, then yeah, this means same investment, same hardware, more revenue. Is that a good problem or is that a bad problem? Often it's a good problem, yeah? And we also need to bear in mind that when you're running these VMs, there are certain considerations. So, for example, you can over-provision the VMs, over-provision the CPUs, but you do not want to go down the path of memory overcommitment. And then what we do is that after we figure out how to rebalance them, we live migrate them, but then after we've live migrated them, what else can we do? Aha! Now we have servers that no longer have any load. So, can you then power down the servers, put them in low power states? Sure you can. And that's what we do. And now, in certain environments, you're now also required to report on your carbon consumption. So that's another thing that we could do with the system by tracking what is the compute resource consumption of the workloads attributed to the VMs, and then with that, we can provide reporting on what's the carbon footprint of the workloads. Of course, it's an estimation, but it is now required for some of the larger organizations. So what we've seen is that when we run this in some of the larger facilities, we're seeing before packing, they have, some of them are running 10 to 35% utilization over a period of time. Does this sound too low? Or is this a typical situation? So I was talking to someone else earlier that there is a particular bank that run a system, 10,000 servers, workload cranks for about 7 to 8 hours a day. 2/3 of the day, it's sitting idle. Until midnight, when data comes in, it cranks again. Come the weekend, it's a glorified heater. There's nothing there. And so when you work it out, it's 35% utilization across the period actually abnormal? No, it isn't. It's a typical working time in a lot of organizations.
There is a good reason for this.
Indeed, there's a good reason for this. Yeah. And in a research facility, they have another type of problem, which is that so the users get allocated VMs, and the user goes off on holiday. Machine is sitting idle. Nothing happens there. It's a glorified heater. So again, you got opportunities to pack the workloads, minimize the number of servers that are needed to cater to that workload set. Ultimately, for the operator, this is about cost reduction. So this is another view looking at it. How many of you are familiar with OpenStack? I see a few hands up. So, in standard OpenStack, what you have is when you take a node, let's say that node has 10 cores. And let's say that you have no CPU over provisioning. So 10 cores, 10 vCPUs, and you allocate 10 VMs, 1 vCPU each. OpenStack says it's full. Nothing else that you can do. And so, as an operator, you may understand that there's nothing happening there, but you still can't do anything about it. So what we do is that we take the equivalent problem that you see in a hotel environment. We look at what is the utilization, and we pack. And we pack. And then, as necessary, we may expand again. Okay? So then, once you consider that you can run the system efficiently, next issue is how do you run the system reliably? Remember, where you have the relationship between the operator and the service consumer being a lot looser, there is higher likelihood of your service consumer pointing a finger when they say, ooh, the system is unreliable. So let's look at traditional monitoring. Traditional monitoring, the principles behind them is that you probe. If the other end responds, say it's all good. Next cycle, you probe again. And it doesn't respond. Not quite sure why. So you probe 3 times, still not responding. Okay, you declare death and you call the operator. Yeah? This is the traditional approach. But now, if you look at that situation, by the time you alert the operator, the system is already affected. Some service is already down. The service consumers, their experience are already affected. So they are going to call you incompetent. Which operator likes to be called incompetent? No, you don't want to be called incompetent, right? You want to deliver a reliable service. So then, now what do we need to do? We take logs and we figure out, is this looking like a picture of health, or is it looking like a picture of sickness? Now, imagine that we're talking about human health. At times, so first off, at times I get asked, well, why don't we redefine the states at the levels at which we alert the operator? If we do that, if we transpose that to the problem of human health, this is equivalent to saying, well, we're going to bury a whole bunch of sneezing people, because that's really redefining states of death, right? So what we want to do is that we take the log data, we take the metrics data, we compose the equivalent of the picture. And then we derive from the picture in a manner similar to when you go to the doctor for human health, you get an image, and you have an automated system to detect, is this a picture of health or is this a picture of sickness? And with that, we can provide the operator with better view on what needs to be done before the problem manifests itself. And this also then helps us to go after understanding what could potentially be wrong in the system. Okay? So that's a quick overview on what we do in Sardina systems, one of the aspects. Thank you.